Okay, three ways to find Bernoulli numbers. But before we dive into the topic, I think there's a necessity for enough for log, like why, how, and everything else. Okay, so most of us have known throughout the childhood that the sum for first and natural numbers, right? One plus three, two plus three up to n, which is n into n plus one by two. If you change this to n minus one, like there will be a slight change that you have to replace n by n minus 1, which is n minus 1 times n by 2, right? And we have also known formulas for the squares, which is n plus 1 to n plus 1 by 6. We also know formula for the cubes, right? Which is n square n plus 1 whole square for 4. And during our childhood, like when we come to the power of 4, and then we get stuck because no one really tells us the formula for this one. And we try to find the formula. We try to express this as polynomials, try to see the pattern, and maybe try to find the pattern so that we can get this polynomial, but you will get some polynomial, but that won't work. Yeah. And yeah, so most of us have been through this journey, but there are people before us who already had been through that and who had discovered what the actual formula is, right? And we just get their contributions and we just use that and we are able to solve the stops. And yeah, we are going to discuss on the same topic today. So here's the formula actually, that sum from 1 to n minus 1 raised to power 4 will be equals to 1 by 5, and then 5 to 0. This b sub k is actually the kth Bernoulli number, right? And we are trying to find that in this video by three ways: generating function, recurrence relation, and direct formula. Okay, so yeah, and the sum for this, the formula for this sum is 1 by 5, 5 to 0, b0 n to the power 5 plus 5 to 1, b1 n to the power 4 plus 5 to 2, b2 n to the power 3 plus 5 to 3, b3 n to the power 2 plus 5 to 4, b4, and yeah. Now this looks exactly like the expansion of 1 plus x to the power 5, right? Let's say 1 plus n to the power 5. Over here, let's write instead b plus n to the power 5. Now this is exactly 5 to 0, b to the power 0 n to the power 5 plus 5 choose 1 b to the power 1 n to the power 4 plus 5 choose 2 b to the power 2 n to the power 3 plus 5 choose 3 b cube n square and blah 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 blah. It is exactly like this. Let's see, here should be node n to the power 5, the combinations b1 n to the power 5, except that this is power of b and this is in subscript. Yeah, so this is not really like a surprising connection or like something random. There's well-known relations or formulas associated with this, and this is not just a coincidence. I just wanted to let you know about that. And this doesn't work only for the power 4. This also works for other powers. Let's say if you want to find it for power 5, that also works. 3 to the power 5 up to n minus 1 to the power 5. Now there will be 6 over here, and 6 to 0, b0, and these numbers are same, b0, b1 are same, n to the power 6 plus 6 to 1, b1, n to the power 5. Now this goes on decreasing, plus 6 to 2, b2, n to the power 4. This goes on up to 6 to 5, b5, and right. And if we generalize this, we can find the sum of our kth powers. Yeah, and this formula will be, notice that there is n minus 1 actually, not up to n. This sum is up to n minus 1 by k plus 1, right? and sum from m equals to 0 to k. Binomial is k plus 1, choose m. M Bernoulli number, and then x to the power k plus 1 minus 1. This is the general formula to find the sum of any powers or that natural numbers are raised to. But how do we find this Bernoulli number, right? Because only if we have that, then we can solve it. So in this video, we will discuss three ways in which we can find the Bernoulli numbers. And I'm just discussing the ways and not the regions behind them. So maybe you might not find it completely satisfying. But yeah, I'll try to do a good job. I don't know. Yeah, let's just go ahead. So first of all, generating functions. Okay. So there's a function whose the function is x divided by a to the power x minus 1. So this generating function will basically be okay. I think it's good to have some Bernoulli numbers at our hand so that we can actually check the values that we find out. Yeah. So let me just write Bernoulli numbers over here so that it will be helpful. Bernoulli number of 0 is 1. Bernoulli number of 1 is minus half. Bernoulli number of 2 is 1/6. Bernoulli number of 3 is 0. 4 is minus 1 by 30. 5 is 0. 6 is 1 by 42. This will be helpful. Yeah. Okay, now let's try to find out. X by e to the power x minus 1 will be equals to sum from n equals to 0 to infinity bn by n factorial x to the power n. This is the generative function for the Bernoulli number because this involves an infinite power series which has Bernoulli number and we have a function for that. Right? Now how can we use this to find the Bernoulli number? Okay, so if we expand this sum, we see that we get b naught by 0 factorial x to the power 0 plus b1 by 1 factorial x to the power 1 plus b2 by 2 factorial x square plus b3 by 3 factorial x cube and so on, right? Now you might have known that, or you can also see it by differentiating, that b0 is actually the derivative of this function, right, over here. Derivative of this function evaluated at 0, right? And b1 is the b0 is not derivative, that's the original function. Now for b1 we need to differentiate this and evaluate at 0, right? For b2 we need to double differentiate this and evaluate at 0, right? I think you know that these are actually the derivatives, and the derivatives evaluated at whatever the center is. So over here the center is 0 because there's x minus 0, right? So in this way I can find it. Let's try to find a few values actually. And b4 will be 4th power of f at 0. Now let's try to find it. So b0 will just evaluate it. So if you just put it over there, we will have 0 by 1 minus 1, which is 0 by 0, right? Which you cannot find. So that's why you have to take limits. If there's indeterminate form, you have to take limits. So we have limit x goes to 0 of x by e to the power x minus 1. Now since this is 0 by 0 form, we can use L'Hopital's rule and differentiate both the numerator and denominator, which gives us 1 by e to the power x, which is 1 by e to the power 0, which is 1. Right? Now let's try to find b1. Okay, so first of all we have to differentiate this expression. We have to differentiate this expression and then evaluate at 0, right? So derivative will be b u dash minus u b dash by b square, right? And evaluate at 0. And this is e to the power x minus 1 minus x e to the power x by e to the power x minus 1 square, evaluated at 0. Again, it seems like we run with an indeterminate problem. So let's take the limits. X goes to 0 e to the power x minus 1 minus x e to the power x divided by e to the power x minus 1 whole square. If you differentiate numerator and denominator, you get e to the power x minus e to the power x minus x e to the power x divided by 2 e to the power x minus 1 times e to the power x, right? Now what you can do is, what can you do? You can basically, let's try to simplify it. Now these two just cancel out, right? And then e to the power x also cancels out, so we have minus x by 2 times e to the power x minus 1, right? So this is minus 1 by 2 times limit x goes to 0, x by e to the power x minus 1. Now we know that this limit is 1 from the previous example, so minus half times 1, which is minus half. So we see that these two values satisfied. Now you can check for remaining values by yourself. Yeah, just again differentiate this and evaluate 0. That's a really easy task. That's actually a hard task, so I'm leaving it. Now second number, using recurrence relation, right? Now this recurrence relation we can get this from the original formula itself. Okay, let me show you how we can get this recurrence relation. The recurrence relation involving the Bernoulli numbers is sum from m equals to 0 to k plus 1, choose m, Bernoulli of m is equals to 0. This is the recurrence relation involving Bernoulli number, and I think you might have seen this expression earlier. So over here I had given you that formula, that the sum when raised to kth power up to n minus 1 term, this is actually 1 by k plus 1, and that sum, right, m equals to 0 to k. Yeah, over here this is not actually x, this is actually n. I'm sorry for writing that x. Yeah, now m equals to 0 to k plus 1, choose m, Bernoulli of m, n to the power k plus 1 minus m, right? So over here, if you want to sum up to n minus 1th term, this formula works, right? Now let's say what if you like just want to sum up to the first term, right? I mean what if you just put n is equals to 0 over here? That means n equals to 1 if you put n equals to 1 over here, you are actually summing up to 0th term, like you are not summing anything at all, right? So if you put n equals to 1 over here in the both sides, there will be sum up to 0th term, and over here on the other side, that will be sum from m equals to 0 to k plus 1, choose m, bm, and this is 1 to the power k plus 1 m minus m, right? Now we know that sum up to like this 0th term, because if n equals to k, the last term will be 0 to the power k, so that means only up to 0th term that we have been summing, so that will be 0, right? This is 0, 1 by k plus 1, and sum from m equals to 0 to k plus 1, choose m, right? And Bernoulli of m, and 1 to the power anything is just 1, and since k is not equals to 0, right, because we are not just summing 1, I think if we just okay, even if k is 0, this still works, because k is not negative number. So since k is greater than -1, in that case this will be a positive number, right? So we can just take it to other side and multiply, right? That gives us our expression, sum from m equals to 1 to k plus 1, choose m, Bernoulli of m, this is equals to 0. So we will use this relation to find Bernoulli number, right? But we will need the initial value, and we will just assume b of 0 is 1. We just know that. Now using this, we can find the remaining Bernoulli numbers. So let's say if you If you want to find this sum for k equals to 1, we get sum from m equals to 0 to 1 of 2 choose m, b of m is equals to 0. So we get 2 choose 0, b of 0 plus 2 choose 1, b of 1 is equals to 0. This is 1, b of 0 is 1 plus this is 2 is equals to 0. So b of 1, 2 times is equals to minus 1, b of 1 is equals to minus 1 by 2. This method is far easier than the previous one. Yeah. Now let's try to find b of 3. So we can take k is equals to 2. In that case, we will have sum from m equals to 0 to k of k plus 1 choose m, b of m is equals to 0, right? Now if k is 2, we will have 3 choose 0, b of 0 plus 3 choose 1, b of 1 plus 3 choose 2, b of 2 is equals to 0. This is actually very interesting property here. The product with the combinations and then their sum is always going to 0. That's interesting. Yeah. Now this is just 1 times b of 0 is 1 plus this is 3 times b of 1 is minus half plus this is again 3 times b of 2 is 0. So 1 minus 3 by 2 plus 3b of 2 is equals to 0. 3b of 2 is equals to 1 by 2. b of 2 is equals to 1 by 6. Now let's do one more because this was really easy and I'm enjoying this. For k equals to 3, sum from m equals to 0 to 3 of k plus 1 choose m, b of k is equals to 0. So this will be 4 choose 0, b of 0 plus 4 choose 1, b of 1 plus 4 choose 2, b of 2 plus 4 choose 3, b of... Is this right? Yeah. b of 3 is equals to 0. 1 into 1 plus 4 into minus half plus 6 into 1 by 6 plus 4 into b of 3 is equals to 0. 1 minus 2 plus 1 plus 4b of 3 is equals to 0. 0 plus 4b of 3 is equals to 0. b of 3 is equals to 0. Now this interesting thing, if you try to find all the Bernoulli numbers, that b of 5 will also be 0, b of 7 will also be 0, b of 9 will also be 0. In fact, all odd Bernoulli numbers will also be 0. That's an interesting thing which I have proved a long time ago in my channel, and you can try to prove that. Yeah, that's an interesting property actually. Now let's go to the third way of finding the Bernoulli numbers, which was direct formula. Many of you would have been excited for this, but this is actually not that elegant. Anyways, it feels good to have direct formula, right? Now the Bernoulli number can be found out by this direct formula. The formula is sum from k equals to 1. Wait, sum from k equals to 1 to n. Oh, sorry. And 1 by k plus 1, and then sum from m equals to 0 to k minus 1 to the power m, k choose m, and then we will have m to the power n. Okay, so sum from k equals to 1 to n, 1 by k plus 1, and then sum from m equals to 0 to k minus 1 to the power m, right? Yeah, there it is. Because there will be alternating signs, so that's what this covers. And then there will be a binomial from k to m, and then we'll have to raise m to the power the initial number. And okay, yeah, that looks good. Now let's try to evaluate this. This is the formula. Try to look for the proof of formula yourself if you want to, right? Okay, now b of 0. We put n equals to 0. Oh, this goes from 0. I'm sorry. Okay, so sum from k equals to 0 to 0. That means the loop will be executed just once. m equals to 0 to k minus 1 to the power m, k choose m to the power n. Now the loop will be executed only for value of k as 0. So this is 1 by, okay, so over here, this is m to the power 0, so that goes to 1 directly. This will be 1 for this case because n is 0, right? Now this is 1 by 0 plus 1, and then sum goes from m equals to 0. So for the first loop, when k is 0, there's 0 over here, minus 1 to the power m, k choose m times 1. So this is 1 by 1. Again, for m equals to 0, minus 1 to the power 0, 0 choose k is 0, right? I forgot to write that over here. I should have written it earlier. Okay, 0 to 0 times 1. We know that 0 to 0 is just 1. So this is 1 times 1 times 1, which is 1, right? Now let's try to find b of 1. b of 1, sum from k equals to 0 to sum from k equals to 0 to n, 1 by k plus 1. Sum from m equals to 0 to k, minus 1 to the power m, k choose m to the power n, right? Now since n is 1, we'll substitute here 1 1. Okay, wait, 1, so no need to write over here 1. So now at k equals to 0, this will be 1 by 0 plus 1. Then sum from m equals to 0 to 0, minus 1 to the power m, 0 choose m, right? Now at k equals to 1, that will be sum at k equals to 1, that will be 1 plus 1, and then sum from m equals to 0 to 1, minus 1 to the power m, 1 choose m, right? Now let's try to find the sum. So the first sum, we know that it's actually, okay, yeah, the first sum is actually 0 now, because initially over here this was 1, so that's why we got the sum as 1 over here, but over here this is not 1. So since this is m and at m equals to 0, this will just go to 0. So the first sum is 0 in this case. And second sum will be half, right? And this remaining thing will be evaluated 2 times. So in the first run, it will be minus 1 to the power 0 times 1 choose 0 times 0, plus in the second round, it will be minus 1 to the power 1 choose 1 times 1, right? This is half, 0 minus 1, so this is minus half. You see that we get the same result anyway, and that's the beauty of maths, right? Okay, so yeah, direct formula also worked. Maybe you can try it from other numbers yourself. Yeah, I think you would want to try that because you already have values, then I think you can find it now, right? And yeah, so these are 3 popular ways. Among these, recurrence is the most popular one because this is the most easier one, right? And yeah, these are 3 ways to find Bernoulli numbers, and I hope that you also understood our prologue, how Bernoulli numbers can be helpful to sum up, right? And yeah, this is it. Thanks for watching. Look forward to seeing in upcoming videos. In upcoming videos, we'll try to sum the alternating natural numbers raised to power k using Euler numbers. That's it.